Welcome friends. Let us continue our discussion on transient response of series RLC circuit. So we have circuit, that is series RLC circuit is connected to a voltage source of V, magnitude V, through a switch S which is initially at open. So it is at open condition at t is equal to 0 minus, and it is closed at t is equal to 0. So from 0 second we consider it from positive time. So let us analyze the circuit. So we directly apply KVL equation. V is equal to RIT plus L di dt plus 1 by C integration 0 to t I dt dt. So if you take derivative, then this first will be d2i dt2, then second this term will be R by L di dt, and this term will be 1 by LC IT, and taking derivative of a constant term is 0, so that is why V becomes 0. So it is a well-known equation of this kind. d2i dt2 A d2i dt2 plus B di dt plus cy, that will be equal to 0. It is the same form actually. So if you compare this, you can get A is equal to 1, B is equal to R by L, and C is equal to 1 by LC. So the solution, as it stated previously, this is the solution. Y is equal to k1 e to the power ct plus k2 e to the power dt, where C and D are the two roots. So just follow that expression. So this is the solution. Yt is equal to k1 e to the power ct plus k2 e to the power dt. Okay. Now what is C and D? C and D, that could be found out by this formula. Okay. So it will be minus R by 2L. So what is that formula? Let me write it down. C and D, it is minus 2A, check, minus B by 2A minus B by 2A plus minus under B square minus 4AC by 2A, root under B square minus 4AC by 2A. So if you substitute, what is B? B is equal to minus R by L, and what is A? 1. So it will be minus R by 2L, that is written, plus minus root under B square. B square is equal to R square by L square minus 4 into 1. A is equal to 1 and C is equal to how much? 1 by LC by 2A. What is 2A? A is 1. So this is the thing. So if you solve this, you will get this expression, minus R by 2L plus minus root under R by 2L whole square minus 1 by LC. Now understand the nature of the solution. It is very important that this relation, actually this three relation is very important. Now to understand, this fact, you please try to get one information that, so if you consider any one of these graphs, you can understand one thing, that any graph, it's starting from something, so initially the rate of rise of the curve is very high, and as the time passes by, then that it after some point of time, it steadies at some certain value. So it, again I am repeating, initially it started and its magnitude changing with a rapid rate, right? That is why this phase is called transient state, and after certain time it steadies its response or its performance, and it steadies itself to a final value. So for every response you will get to see that, whether you can observe IT or VRT or VLT or VCT, you will see same this kind of response. And now coming back to this nature, now you see this R by 2L whole square can be equal to 1 by LC depending on the value of RLC. It again, R by 2L whole square may be greater than 1 by LC. Again, it may be less than 1 by LC. It totally depends on the value of RLC with which we are design our circuit. So if they are equal, then it is called critically damped. Right? Now if it is a greater than 1 by LC, then it is called over damped, and if it is the less than 1 by LC, then it is called under damped. Now what is the meaning of these terms, damping? Let us try to understand. Let us say that we want to observe the response of a current. We want to observe a response of a current. Now, as far as the nature of current or voltage, whatever it may be, is concerned, it finally settles down to a value. Let us say that value is I, and initially it will start from 0. Now let me first tell you, or let me first plot this curve when it is under damped case. That means it will roughly follow this nature. The rate of rise is large, then it will go past its steady value, then again it can come back, then it goes like this. Ultimately in this way it will settle down. It's in this way. After some point of time it will settle down. Now this type of response is called underdamped response. This type of response is called underdamped response. Okay. So again I am repeating, initially the rate of rise is large, but it will not stay at its steady state at the initial instant. It will pass that value, it will over that value. After some point again it will come back, and again it will be reduced with respect to its final steady state value. And in this way, as the time passes by, its intensity of the oscillation reduces, and finally it will settle down to a steady state value. Okay, this response is called underdamped response. Now if you follow this case, that is equal to case, if you follow this case, equal to case, that is, it is called critically damped response. So we will roughly see this nature. It will straight going to and settle to this value. Okay, settle to this value. So this response is called critically damped. critically damped. Now lastly we have another response, which is this case overdamped, which is r by 12 whole square is greater than 1 by LC. So it will roughly take this nature. So this is actually called damped case. Now what are the differences between these three responses? First of all, if you observe this overdamped case, it reaches large time. It requires large time to obtain its steady state value. So for overdamped case, the system is very sluggish, slow in nature, very sluggish. Now the critically damped case, you see that the response it is reaching to the steady state value relatively in a faster way. Okay, so critically damped system is less sluggish. However, in the first case, underdamped case, it will get around the same value, but you will observe this is overshoot, this is called overshoot, right? This spike, this is called undershoot. You will observe lot of these issues, and you will get to see that the response is settled down after some point of time. This is the nature of the underdamped case. So most of the times our system, by virtue of system element, most of the times our system is underdamped. In nature. We will follow this type of nature. Okay, in different applications of electrical engineering. So this is the meaning of overdamped, critically damped, and underdamped. We will respond and we will observe these three types of nature. Now that out of these three terms, one term is very common, that is damping. Damping is common. Okay, so what does it mean? What does this term mean, damping? Okay, damping means from the very inception of this chapter, I have started saying that whenever, not even for this chapter, whenever you come across some disturbances, it will bother you. So it takes some time to overcome that. It is a natural process. Okay, I have cited one example that if you are staying in a dark room and suddenly if you come to the sunlight, then your eye will be not compatible to the certain change. Your eye will feel discomfort. That is called transient state. Now slowly your eye should be accustomed to that change in environment. Now from slowly your eye is getting accustomed to this environment. So from that transient state it is going to the steady state. Slowly this is mainly because of your damping of the system. So damping is the natural thing which will create some pulling force to die the transient force, right? That means that force which creates the mainly transient behavior, that means the sharp disturbances are there, that your system damping will die those disturbances. That's it. Okay, so it is a fundamental concept, it is universal concept, you can apply anywhere. So when a transient state occurs, when a transient state occurs, then it reaches to steady state. From transient state it reaches steady state. Okay, and it requires some time. It will not do over the time, instantaneously it will not work, but it will require some time. Okay, some time, t is equal to infinity, right? So the main cause of doing this, from bringing one system from transient state to steady state, is because of damping, because system is having inherent damping. Without damping, no system can be converted from transient state or can be brought from transient state to steady state. Okay, so damping actually does what? Damping will die or will make weaken your these oscillations, right? These oscillations. So here damping actually the key factor which brings your system from transient state to steady state. Now, who creates the damping? This is the main question. First question is that what is damping? So damping is that natural force which dies the transient behavior slowly, not rapidly, right? Now, who creates the damping? The question comes, this network has 3 elements RLC. Out of these 3, who creates damping? The answer is the resistance will create damping. Out of this, resistance will create damping. Without resistance, no system is having damping in it. Okay, so when you respond or when you observe a system with a overdamped response, that means its system's resistance value is too large, extremely large. When a system that is observing underdamped response, that means its resistance is very low. It has damping, but it is low. Okay. Now, ideally, every system or especially electrical system must have some damping. However, ideally, if we consider that with a zero resistance system, if R is zero, then that means we have no damping. Ideally, theoretically, we have no damping. Then what will be the response? As compared to with these 3 ones? So if a system having no damping, then your response will be like this. Okay, your response or your oscillation will never die out. So this type of response is called undamped response. Undamped response will never die. This type of response will never die. It will continue like this. It stays for a long time, t is equal to infinity. Neither intensity will increase nor decrease, because R is 0. There is no one to damp that oscillation. Okay, or damping means weaken, to make weaken. So we have understood that. So there are the 4 types of responses. Mainly we have come across underdamped response. Mostly there are very few instances where we use critically damped or overdamped response, and ideally or theoretically, if we have R is equal to 0 for our electrical system, then we shall see this type of response, which is called undamped response. Undamped response means we have no damping in our system. So with this, we are ending this part. We have understood that different types of response for a series RLC circuit, and it is totally dependent, the type of damping is totally depending on the value of RLC that we have chosen for a particular application. So with this I am ending here. We shall solve some problems in the next session of this course. Thank you.